Discrete text diffusion promised a new way to generate language, fluidly negotiating all words simultaneously before solidifying them. But in practice, current models experience a form of sublimation. They skip the liquid phase entirely, snapping directly from a maximum entropy cloud of uniform noise straight into solid committed tokens. Skipping that intermediate state carries a severe penalty. It prevents the model from holding a superposition of likely meanings across multiple denoising steps. When engineers attempt to force the model to keep positions open longer by artificially lowering the confidence thresholds required to commit, the result is not a steerable, coherent text negotiation. The outputs simply boil off into random, uncorrelated noise, effectively turning into steam. The bottleneck is structural. We are witnessing a breakdown in the concept of diffusion because of exactly where our current architecture allows us to intervene. Attempting to control uncertainty at the end of the generation pipeline makes contextual reasoning impossible. We are operating on the wrong side of the model. The architecture of a uniform state model like DiffusionGemma maps out a specific limitation. Our tools target 6 distinct points of intervention, all clustered at the pipeline's end. Constraints applied at these output seams function strictly as a binary gate. The model must commit definitively to a specific token, or reset that position completely to uniform noise. Tracing the pipeline back to its origin reveals a single, untapped point of entry, the input embedding seam. Because the output side is mathematically incapable of holding a multi-step distributional belief, the model has no choice but to jump from noise to solid text. To maintain textual superposition, where unfixed tokens conditionally adapt to the uncertainty of their neighbors, the intervention must occur at that input embedding seam. Recent literature offers empirical proof that this input seam intervention works. Models utilizing latent refinement decoding and soft masked diffusion directly solve the superposition problem. This diagram illustrates rejecting the binary mask or word choice. The top shows the baseline, a hard mask or unmask decision. Below, Phase 1 introduces mixed tokens, gradient blocks formed through continuous interpolation. The model iteratively refines distributions without committing, transitioning to solid commitments only in Phase 2. This is soft diffusion. The uncertainty operates entirely in the continuous embedding space, rather than forcing a discrete choice in the token space. Within this soft space, self-attention changes. Tokens no longer look at hard assignments. Instead, they condition their own predictions on the continuous belief states of every other position. By moving uncertainty into the embeddings, masked diffusion models create a liquid phase. Contextual errors can be smoothed out in a state of superposition before any single word freezes into text. The mathematical engine driving this soft diffusion relies on equation 3. It splits the embedding into two halves, the mask embedding weight on the left and the predicted token weight on the right. The alpha coefficient balances them, preserving exploration in high uncertainty positions. Applying this mathematics to a uniform state model like DiffusionGemma hits a barrier. They possess no trained mask anchor. We could try a translation by swapping that mask variable for E-bar, the expected embedding of a uniform mixture of all possible tokens. However, an LLM's latent space is a sparse cloud of specific high-dimensional points. Taking a mathematical average, that E-bar anchor, lands the model in a semantic dead zone. This landing is off-manifold, a region where the model's weights have never been calibrated. Without continued pre-training, the model interprets E-bar as garbage, making immediate deployment impossible. Without a continuous latent field, we engineer a proxy. We achieve local constraint propagation decoupled from the embedding space. Focusing here, we construct a crystalline cellular automaton over solid tokens. Each position rapidly flips through a discrete list of candidates until it lands. To enforce specific local rules, like a word game viability check, we return to the output side of the pipeline and apply dynamic logic masking. When a cell finally commits to a token, it acts as a thermal trigger. It executes a local remelt, briefly re-annealing its immediate neighbors, forcing them to adapt to this newly committed constraint. This local remelt sidesteps the sublimation problem. It treats the text as an array of linked solid crystals that structurally adjust to one another, rather than a single pool of liquid. This crystalline approach proves we can enforce complex logic right now. By utilizing existing output seams, we simulate sophisticated constraint propagation without modifying weights. This discrete system maintains coherence because of a division of labor. The cellular automaton enforces the strict topological rules locally, while the model's inherent global bidirectional attention ensures the semantic meaning remains sound. Currently, we rely on these output-side mechanisms, using dynamic masking and local remelts to construct rigid, crystalline constraints. This crystalline setup is a powerful proxy, but moving the architectural boundary to the input embedding seam remains the next logical transition. Shifting intervention to the embeddings allows the model to capture global distributional information at the source, smoothing out its logic before the first token forms.